Okay, so we're going to revisit the Newton step direction later on, or the step size and direction, the step vector. We're going to revisit it later on in some of the optimization methods that we're going to cover. But next I would like to now consider the trust regions, or to add the trust regions, or at least to discuss why we need those intuitively. So let's assume that our approximation function is a second order Taylor polynomial, right, as defined here. And of course it's defined now with gradients and a Hessian matrix, because usually we perform high dimensional optimization, right? Our policy might include many tunable parameters. The closer we are, as we've seen before, the closer we are to C, usually our approximation is more accurate. We saw some of these videos before. And this is why we would like to add trust regions, those regions where we trust our approximation function to be closer to the real function. These are usually defined as a hypersphere, for instance, using an L2 norm, and defining the distance between our known point, can be a policy in our cases, policy that is defined by many tunable parameters, and the optimal point that we would like to move to, right, within the trust region. We just require that this change, the change to all of the tunable parameters in our policy, for instance the L2 norm between these two vectors, is lower or equal to some trust region that we define. Okay, we can define it using small delta in this case. But of course it might be that there is no local optimum within the trusted region. We see that a lot with constraint optimization, where the optimal point sits on the bound of the constraint, where your constraint is active, if you remember your Lagrangian optimization. That is, you will find no point with a derivative of 0. You will find no local optimum. And so we're going to use, as we said before, the Lagrange method to set the trust boundaries, and also to solve the optimization problem, the constraint optimization problem. Right? Because Lagrange method can provide us with the optimum under constraints. It's usually used to do so. So now we can discuss a very generic algorithm for a trust region method. Later on we'll go a bit deeper into the details, but the general idea is actually pretty simple. We initialize our trust region, some initial assignment, we hope. Well, it's not necessarily the optimal one, right? We'd like to converge on the optimal one. And this, in our case, can be a policy that we initialize. And n, which is, what is n in our case here?
The number of steps? Time steps?
Yes, repeat for n times. No, but there's no stopping condition.
Until convergence.
But what's n? Okay, so we can now define a very simple approach for performing trust region based optimization. Right, it's a simple approach, more intuitive. Later on we'll dive more into the details. So we start by initializing our trust region. Some initial assignment to our tunable parameters, right? Those that we would like to find the optimal with respect to. And we'll set our the step size to 0, and of course we'll do it in iterations. So we'll start with iteration 0. So at each iteration, we solve for our approximated function, or we solve we solve for the optimal assignment for x in our approximated function under the constraint where the return value, the new x value, the new x assignment, is within a bounded distance from our previous guess, from our previous x assignment. Of course, the distance is, in this case the L2 distance, is bounded by the delta hyperparameter. And of course we can keep the delta hyperparameter dynamic. We don't have to keep it constant. For instance, if the approximated solution, right, now we can take our solution and evaluate it in the real world. And if we see that the approximation for that value is indeed very close to the true value from our real function, then we can increase delta. We can say that our approximator is actually pretty useful for the defined region. Else we decrease the trusted region. Okay, so we can play with the trusted region based on the observed outcomes that we see for each iteration.